Hi everyone, so let's talk about chapter 10.2, Fourier Series. We know we can represent arbitrary functions using powers of x, such as the Taylor series, but we can also represent them using sines and cosines, what's called the Fourier series. So this is the expression of a Fourier series, and we're going to talk about what is this L right here. And we're going to talk about how to calculate AN, A naught, and BN. So let's talk about what it means to be a periodic function. A periodic function means that f of x is equal to f of x plus t, where t here is the period. So let's kind of try to understand what this means. Let's take an example of a periodic function such as f of x is equal to sine of x. So we're going to give this example, f of x equals sine of x. So this is the function y equals sine of x. Let's choose an arbitrary point, x naught, for example. If we choose an arbitrary point, x naught, let's say the maximum point of sine of x. Let's say that this point right here is x naught. We also have a corresponding f of x naught, right? And what a periodic function does, it says that if you take an arbitrary point x naught and you have a corresponding y value, f of x naught, if you add a period to this point, so let's add the period of sine of x is 2 pi, that's the fundamental period, that's the least possible period that makes it periodic. So let's say t equals 2 pi in this case. So here at this point, x naught plus 2 pi, which is the period, is also going to give us, the output is also going to be f of x naught. So this is how we can visualize it. You get any arbitrary point here, x naught, and if you shift a whole period, it has to go to the same output. This is how we can visualizing using sine of x. But of course there are many different types of periodic functions, but it's just something to visualize. But the L here in this case is usually the period divided by 2. But in many of the questions that we're going to solve, we can usually know what the L is by the way the problem is written. Most of the times it's going to give us a boundary and we can kind of see what that is. But that's going to become clearer when we solve an example. I'm going to write down the problem. We're going to talk about how do we know what the L is. So a way to visualize that L is generally going to be the period over 2 is that we're going to construct the function in the following way. Let's consider the same graph, sine of x, but let's consider on an integral negative pi to pi. So this is the same function, y is equal to sine of x, and we're going to consider it on an interval negative pi to pi. So what is the period of this function? Well, the period is going to be 2 pi. But the L, usually we're gonna look from the origin to like our bound. So it's gonna be our period divided by 2. So the L is gonna be 2 pi divided by 2, which is pi. So it's generally gonna be symmetric. It's generally gonna be symmetric from negative L to L. And we consider it from 0 to pi. So let's work through some examples, and that's going to become a lot clearer. Now let's talk about the second part. We wanted to know, how do we calculate a sub naught, a sub n, and b sub n? Well, if you want to understand a little bit more why, like how to arrive in these expressions, again, you could always look at page 599, 598. It goes through the derivations, but what we need to know is, how do we use them? So these are the expressions that give us a sub naught, a sub n, b sub n. We're going to use the properties of odd and even functions a lot in this chapter, because when we know a function is odd or even, that's going to make our calculations a lot simpler. For example, if we know that the function is odd and we're integrating from negative L to L, we automatically know that that expression is going to be 0. However, if we knew that the function is even and we're integrating from negative L to L, then we know that this expression is going to be equal to twice the integral from 0 to L of this expression. So that's why I made the other video on properties of odd and even functions. It's going to help us a lot in the calculations. There's also a lot of integration by parts in this chapter, so make sure to review on that. Here is the integration by parts. Is the integral of a function times its derivative is equal to the product of the two functions minus the second function times the derivative of the first function. So this is the integration by parts formula. Might be important to memorize this. And it's how we solve many of the problems. I'm going to go ahead and start our first example in the next video. I'll see you there.